Good afternoon, everyone. Thank you for coming. We've got our lecture now in the series of the Sustainable Nano Seminars, which is organized by the Spanish Network on Safe and Sustainable Nanotechnologies, which is coordinated by the ICN2. Today, Riccardo Rurali here from the ICMAB will be talking about thermal conductivity by design. Riccardo did his degrees in Milan and then his PhD from the UAB, but working at the Institute of Microelectronics just across the road from here, where he studied modeling defects in silicon carbide. He then did a postdoc in France at the Université Paul Sabatier on surface science simulation. Then he came back to the UAB and eventually got a permanent position here in the ICMAB, where he's carrying out his research now into molecular simulation. So Riccardo, it's great you did this talk. Thanks very much.
Thank you.
Look forward to hearing it.
So I'm supposed to stay here so people can see me, I guess. Okay, so thanks for coming. The goal here is giving you a lecture about what I do, but also trying to give some broader perspective on the fundamentals of heat transport, the way at least I see it. I do theoretical simulations, so everything will have a theoretical angle, but of course there will be no details whatsoever on the real calculations that we do. These are okay. Okay. So these are the usual three big motivations that I choose to illustrate the interest in studying heat transport at the nanoscale. The first one is the one which is most directly related to the topic of this network, so sustainability, and concerns the design of thermoelectric devices, which are devices that are able to convert heat into electricity. And then we have these other two boxes. That a way to see them is that the thermal management deals with the present time information technology, so electronics, and the main problematic related to electronics nowadays is that because the miniaturization of the devices, you have to be able to evacuate heat efficiently, so cool the devices down efficiently. And this other one, if you want to be a little bit optimistic, is the information technology of the future, or at least one of the possibilities, which is to process information with heat carriers rather than charge carriers. And I will say something later on if time permits. Still, this is also quite related with sustainability issues because it is now currently the main bottleneck that prevents to have efficient electronic devices. So nowadays, the real bottleneck in electronics is no longer the usual more low that dictates the speed at which we are able to miniaturize electronic devices. So companies would be able, in principle, already today to have processors that performs at higher clock frequencies than the one that we have in our computers. But this is not possible because of what is called the thermal bottleneck. So these devices would warm up too quickly, and so they cannot operate. And so here at our institute and our group, theory group, we tackle these challenges following different lines. And this is just a random selection of some of the things to do. It's just an excuse to put some color picture here. Okay, so I was a bit quick talking about heat transport and transfer in general. In reality, there are different mechanisms that you can use to transfer heat. So you have conduction, which is the most relevant in solid. You have convection for liquid and gases, and radiation, which is important when you are in the high temperature and near field limit. Today, we will only address a very little tiny bit of this puzzle, which is what I do. So it's conduction in crystalline solids that are insulating. Okay, so where all the contribution to heat transport is carried by phonons. I am an electrical engineer. I studied phonons at the university, so I assume that all of you have seen something like that, even chemists, you know. Phonons are the quanta of a vibration of the crystal lattice. And so at one point or another of your academic career, you have studied the monatomic chain, the atomic chain, and computed this phonon dispersion. Okay. The way I like to see phonon transport, so the way you transfer heat by means of phonons is with this analogy of the phonon train. So you want to carry energy from one point to the other. You carry this energy on a phonon train. And so for this train to be efficient, you want it to be fast. Okay, so you need high phonon velocities. Okay, which is the bit of this the formula that gives you the thermal conductivity. You want to carry a lot of people on this train. And if you really want to push the analogy with all the elements of this formula here, you want to a lot of people carrying, for instance, a lot of money. So assuming that you want to carry money from one point to the other. So F here is the density of people that you have, and this H nu is the energy that each of them carries in the pocket. Okay, and so this is what is known the heat capacity. And then you want this train to stop not too frequently, because every time that the train stops, there is a delay, and so your energy flux is not that efficient. Okay, so these are all the bits at play here. Usually, if you want to design a material with the thermal conductivity that you are interested in, the main factor that you can act on is the lifetime. So the times that phonons live between one scattering event and the other, and so the number of stops of your train. So if you come here by Rodalias, you know that it does a lot of stops, and so if it did less stops, it would be quicker. Okay, so what does determine the frequency with which this phonon train stops? There are several mechanisms at play. The main one is the phonon-phonon scattering. So the scattering that each phonon gives mutually with each other. So if you want to keep with the analogy of the train, when there is a lot of people, okay, you want to have a lot of people because then your cars in the train will be full of people and you will transfer a lot of energy. But if it's really many people, when they try to get on and off at each train stops, they will just make annoying each other, and so this will slow down and every stop will be slower. Okay, so this is the main scattering that you have in material, and it's a kind of the built-in reason for the thermal conductivity not to be infinite, because all the other scattering mechanisms that we will see in the next slide, at least ideally, you can get rid of, or at least I can get rid of them in my computer. In experiments, a bit more tricky, but conceptually you can think of a world where this other source of scatterings disappear. But this is not, this is always there because this is a built-in feature of the material, okay? The other mechanisms are essentially have to deal with imperfection of the crystal lattice or boundaries, which in a way are still an imperfection of the crystal lattice, because normally when you think of a crystal lattice, you think of something which is infinite, but in real life, in the lab, samples have a finite size, okay? And now we'll see a little bit these different scattering mechanisms one by one with some simple example. So if you want to design a material with a given thermal conductivity, you should be able to act on one of these, one or more this source of scattering, okay? So let me show you some example of how you can do that. These are again quasi-random selection of work that I've done or something that I pick up from the literature. So if you want to a possibility to act directly on the phonon-phonon scattering, so of the anharmonicity of the material, is for instance applying strain. If you apply strain, you change the strength of the bond because you bring atoms to be closer or farther apart, and therefore the efficiency of some of the phonon-phonon scattering mechanisms can change, in general will change. or you can just try to act on some phase change. This is an example. It's not really a phase change, but it is a phase change in a way. These are two different polymers of silicon, the usual cubic silicon, the one that we have in all the devices that we carry in our pockets or in this computer. So usual silicon that you use in microelectronic industry. And this is an hexagonal polytype of silicon, which can be obtained in extreme conditions like high pressure or especially high pressure, but then nowadays has become also available when you grow silicon in the form of nanowires. These cloudy plots here are the scattering rate. So now you don't want to know the details, but when you see many points and high intensity, it means that you have a higher probability of scattering between phonons and phonons. And as you can see, there is a considerable difference between two different polymers of the same material, okay? But then in general, you can think of having a given material and being able to trigger a phase transition between different crystal lattices. Phonons will be different, and then all the phonon-phonon processes will also be different. Defects is perhaps the most intuitive way of thinking about scattering, because this is also applies to the case of electron transport. So you can have, well, I've selected an example, something we did some years ago for silicon. This is well, as the name suggests, is silicon with holes in it, mesoscopic holes in it. And these holes will act as scattering center and will prevent phonon transport to some extent, depending on the distribution and the size of the hole. This is an example a little bit more recent where we studied the ternary alloys. So once you create an alloy, you no longer have a perfect crystal where some given phonons are eigenstates of that crystal, and so all the perturbation of that ideal crystal will scatter phonons. And then you have the prototypical example of scattering by defect in a crystal, which is isotope scattering. This is a very specific defect which is specific to phonons. In this case, this is a strontium titanate in this illustration here, and you have two different isotopes of oxygen. So it's still oxygen, but the mass is different because you have different number of neutrons. So phonons will be sensitive to masses, while electrons, to a first approximation, don't care. And so this is actually a very convenient scheme to suppress phonon transport, but to preserve electron conductivity, which is what you need in the case of thermoelectricity, the very first example I showed in my first slide. Where these are materials that, to convert efficiently heat into electricity, are supposed to have a high electrical conductivity and a low thermal conductivity. So this is it's not that simple and that cheap or convenient to do in the lab, but at least conceptually is the best way to design thermoelectric materials, because it's the simplest way to hurt only phonons and not electrons. Otherwise, these two magnitudes are often correlated. And this is the case of boundary scattering. You can think about other confined systems, but I've been working with nanowires for some time. And although these are not examples of my work, this is the most cited paper in Applied Physics Letters. It's a nice paper where they compute, they measure the thermal conductivity as a function of temperature of nanowires, so filamentary forms of semiconductor. This is our silicon nanowire, so nanoscopic cylinder of silicon, where depending on the diameter, you have a completely different behavior. So not only the thermal conductivity is different, but even the shape of the thermal conductivity as a function of temperature is different. Okay, so this is like a textbook example of how you can tune the thermal properties of a material. Okay, and then of course, once you confine it, you can do more fancier things, like here they have this sawtooth faceting and stuff like that. The same principle applied to like thin films or any system where phonons will not experience as infinite. Okay. And then still, if you want to play, it's not really boundaries, but still playing with interfaces, you can think about stacking interfaces in order fashion and see if you're able to capture some subtler effects. So imagine if you have an interface between two different materials. So you have phonons here in the white part. These phonons are the eigenstates of this white part, so they travel in principle unperturbed. Well, of course, they will suffer phonon-phonon scattering between them. But then when they hit the interfaces, they will be scattered by the interface. Okay, this is like, I mean, any similar scheme with photons or phonons. They hit the interface, so part of them will be transmitted, part of them will be reflected. Okay, so this is a source of scattering. Okay, like in a way the boundary of nanowire. Now, what happens if you stack many interfaces one after the other? In principle, if these interfaces are stacked coherently, you can experience, they are stacked periodically, you can experience some degree of coherent phonon transport. What do I mean with that? So imagine that you have an interface here, I'm a phonon, I'm traveling towards the interface, I'm scattered by the interface, right? And then, okay, after scattering, I recover, then I start traveling again, and then I hit another interface down there. The process will be repeated, will be similar to this one, okay? But if these interfaces are very close to each other, and I'm a phonon, so you know I'm a wave, and my mean free path is much longer than the separation between the interface, I will not really see individual interface. I will just experience one single metamaterial with given properties. So it is possible, and people did that, to do experiments with that. These are experiments that our collaborators in Switzerland did with gallium phosphide, gallium arsenide superlattice nanowire, where they were able to vary the periodicity of the superlattice. Okay, so look at this plot. Here, the period is larger, so interfaces have a large separation. Subsequent interfaces have a large separation between them. Okay, and so all scattering events are independent. Okay, then I start reducing the separation, so the density of interfaces increases. Okay, and if it increases, I have more scattering. And indeed, the thermal conductivity goes down. Okay, so now we are in this regime, incoherent scattering, interface scattering. So each interface is independent. So if you double the number of interfaces, you like double the scattering suffered by phonons. But then when you start reducing again, you can get to this coherent regime where phonons start seeing all the scattering, individual scattering centers, and just see a material with given properties. And then it's when the thermal conductivity increases again. And seeing this minimum is the smoking gun of this coherence effect, which is kicking in. Okay, these are experiments, or this is the real thing, and these are our calculations that, I mean, they are also the real thing, but they are done in the computer, and more or less they capture the behavior of these superlattices. Okay, so by now I should check. Okay, I'm doing quite good. Okay, so so far I presented you examples of strategies to design materials with a given thermal conductivity. This is, well, you know, difficult enough, but we would like to do in principle something more. So if you think about the example I've shown, defects, anharmonicity, boundaries, these are all irreversible design tools that you have at your disposal. Okay, so if you engineer a distribution of defects, then the defects are there. Okay, in principle you cannot get rid of the defects. If you design or you grow in your CVD chamber a nanowire with 50 nanometers diameter, then the diameter is fixed and cannot change. Okay, and so I mean you're good because you were able to design a material with the thermal conductivity you wanted, but the thermal conductivity is then fixed. Okay, so now I would like to show you something that try to goes a little bit farther and try to design materials where the thermal conductivity can be modulated dynamically. Okay, in this case, my motivation is this last box. So you know, something related to information theory where you would like to use phonons rather than electrons or phonons to encode information and carry information. And so this is in principle the same thing that you do with the charge carriers or with photons or electromagnetic waves. You want to carry energy in a controlled way. So you want to be able to modulate this transmission because you want to encode signals. And to do that, you must be able to dynamically alter it while your device is operating. Okay. It has been argued that a very good reason why we do not live in a phononic world is that phonons have no mass and no net charge. And so it's not that simple to tell a phonon what to do like you can do with the charge carrier, with electrons or holes in semiconductors, or with photons in optical communication. Okay. However, I would like to discuss a few examples to show that this is not entirely true. And at least to some extent, something can be. The simple material I choose to illustrate these things is a ferroelectric perovskite. This is a material that at high temperature has a cubic structure, okay? But below a given critical temperature, which in the case I speak here, which is lead titanate, it's a prototypical ferroelectric perovskite. The lattice favors a distortion where this, a green atom, rather than sitting in the middle of the cube, displaces off center. And why are we interested in this distortion? Because each of these atoms has a different nominal charge associated. And so this distortion has a permanent dipole moment associated. So there is a polarization. And this polarization can be manipulated, for instance, with an electric field. So if you take this case, this is the ferroelectric ground state of your perovskite. You apply an electric field which is opposite to it. Oops. Okay. And you switch it, okay? Now, this switch is not that interesting because these two ground states are equivalent. So it's just the same material upside down, okay? But at least it shows you that you can manipulate the lattice. So one of the things that you can do is that you can think of this situation. You have a material where all the ferroelectric distortion points in the same direction. For instance, all the distortion is upward, okay? And then you are able, and indeed you can do that experimentally. Of course, it's very easy for me to do it in my computer. What you can do is that, for instance, you use an electric field and you switch the polarization in half of the material. So then you create a boundary here, okay, which is between half of material where polarization is up and the other half where the polarization is down. And this boundary has an associated thermal resistance, okay? So it is just the same case of this, the incoherent phonon transfer I showed you before, but there the interfaces comes from a change in the chemical identity of the constituent species. Here is something that you can write and erase with an electric field. So you can encode a high conductivity state where the monodomain, all polarization are up, and the low conductivity state where half of the material is down, and so you have written one domain wall. And then if you are smart enough, you can write more domain walls and you can, in principle, encode different level of conductivity, okay? So that's one possibility. The other one that we explored when we started with studying this material, this is a bit old results, but I think they are the best to convey the general idea, how you can manipulate the lattice with an external field. So in this case, I mean, you still wanted to do this trick, but you want to apply a field which is lower than the coercive field. The coercive field is the minimum field that you need to switch the material, okay? So if we do that, for instance, we try to apply an electric field that goes in the same direction of the polarization, so you stretch it a little bit more, or goes against it, so you dump it. And in this second case, you have to be careful because if you push too much, you will switch it. And this is not what you want to do now. So we did that. But of course, first we computed the thermal conductivity of lead titanate in this case without any applied field. Okay, so these are the two independent components of the thermal conductivity tensor because this is a tetragonal material. So you have two directions in the plane that are equivalent and one out of the plane which is inequivalent. So you have two different values for thermal conductivity. It's an anisotropic material. Then you apply your electric field and you see that when you go in the same direction of the polarization, the thermal conductivity goes consistently up. And when you go against it, it goes consistently down. These are the red and the blue curves. And if you take a cut at a given temperature, you will see that more or less there is a linear dependence between the applied electric field and the thermal conductivity. Changes are sizable. They are not huge, but at least it's a proof of concept that you can indeed manipulate the lattice, and this manipulation will translate into the change in the thermal properties. And then with something similar, applying an electric field that goes in the perpendicular direction. Okay, in these cases, the changes are even larger. Here I have 3 panels, because once you start, you make processing the polarization, then all the direction becoming equivalent, because these two were equivalent before, but then if the polarization does not stand in the Z direction, let's say, and has a certain angle, these two become inequivalent. So you have 3 different values, and these are the changes that you have as a function of the applied field. So again, this is a proof of concept that you can change the thermal properties. What is interesting is that in these cases I illustrated, although I didn't discuss in detail, the physical mechanisms that bring upon this change in the thermal properties are different. So in one case, you have boundary scattering. You are able to write and erase a boundary. In the case of the electric field, which is parallel or antiparallel to the polarization, you have a rather simple mechanism where you harden or soften all the phonon modes. So all the frequency goes up or goes a little bit down. In the case of the rotation, the physics is different. You reduce the symmetry of the lattice, and so you lift mean degeneracies, so you have more phonon modes. And if you have more phonon modes, more inequivalent phonon modes, you have more possibility to have this scattering, phonon scattering mechanism. Okay, well, as it works with the electric field, we also thought about doing this with magnetic. Sure.
There is no domain structure.
So
the previous slide.
So no, here it's the monodomain. Yes,
okay.
It's the monodomain. So in these cases, I consider the role of domains here. Okay, and in these other two, it's exactly. So also the difference is that with the domain, in principle, at least ideally, you just have to switch the material, and when it's switched, it's switched. Okay. In the other case, as you have this continuous modulation, you have to keep the electric field on. So maybe it's not the best sustainability-wise strategy, because if you use an electric field to make like a 10 degrees rotation or polarization, when you remove the electric field, the polarization will go back. So if you want that thermal conductivity, you should keep the electric field on. Okay, this is of course a limitation, and one could think about alternative to it. This is I'm not discussing this in the interest of time, but we started exploring also the possibility to use magnetic fields in magnetic materials, in analogy to how we just used electric fields in polar materials. This is a situation that we ambitiously termed as multiphononic, because this is a material which is polar and magnetic at the same time, and it has this magical phase transition where you go from we transition between two phases that are antiferromagnetic and ferromagnetic, not so polar and considerably polar. So in principle, you can switch this phase transition with an electric field or with a magnetic field. Okay, and in this case, we at least predicted a very large change in the thermal conductivity. I mean, if you're interested, we can discuss about this later, but now I prefer to move to the last things that I wanted to show you today. So let me go back to this cartoon that I showed in the beginning. I made some correction because this effect that I will show you now, it's not observed with lead titanate, so everything will be with potassium niobate. It has the same perovskite structure, just a different critical temperature, but it's the same thing. So what in principle you cannot easily do is accessing the paraelectric state, so the cubic phase, okay? I mean, it's not that difficult, you just increase the temperature, okay? If you increase enough the temperature, you will have this phase transition. And so if what you're concerned with is the dynamical modulation of thermal conductivity, here you go, that's it. You just use the temperature as your control signal, your gate signal in the transistor. You increase the temperature, and then you will trigger this phase transition. These two guys are supposed to have different thermal conductivity, and there you go. However, using a temperature to control like a phononic devices doesn't seem to be a very smart strategy. You expect to have a very slow response, and especially everything will happen in this case at 400 Kelvin. Okay, so ideally you would like to be able to do something similar, but you would like to be able to access the cubic phase at any given temperature. So fortunately, there is this existing alternative, which is related to the use of light and photoexcitation. So the physics is in principle rather simple. If you illuminate your material, you take some charge from the valence band, you put it in the conduction band. This charge in the conduction band is mobile and then can screen this long-range dipole-dipole order that sustain the ferroelectric distortion. So when you do that, you obtain the same effect than temperature, although the physical reason is different, and you stabilize the cubic phase. Okay, so in principle, you can switch back and forth the ferroelectric, the polar and the non-polar phase by switching light on and off. Okay, so this is of course interesting because if assuming that, and by now we don't know it yet, we have to compute it or make an experiment. If the change is sizable, you can access these changes to different conductivity state with light at any temperature, in principle. I mean, as long as you are below the critical temperature, so your ground state is ferroelectric, and you can suppress the ferroelectricity and bring it back on. Okay, so this is an appealing situation. And you can see here the physics of this stabilization, light-induced stabilization here. These are the phonon dispersion of the cubic phase of potassium niobate. And when you compute phonons, when you have negative phonon band, this is a signature of a dynamical instability. Okay, so you do your calculation, everything is stable, you have a total energy, but that's it's like a saddle point, right? The derivative is zero, but as soon as you perturb minimal the equilibrium, so in any temperature above 0 Kelvin, you will start moving farther apart from the equilibrium indefinitely. Okay, it's in a stable equilibrium point. So we recomputed the phonon dispersion for increasing density of a charge in the conduction band, and at some point, bang, you stabilize it and you recover a very well-behaved phonon dispersion where all the phonon branches have a positive energy. Okay, so now that we know how to do that, we computed the thermal conductivity to see if we were lucky, because it's very difficult to have make a educated guess before running a calculation. These are rather heavy and time-consuming calculation, but I mean, in the end, you did it. And so this is the change that we have between the blue is the thermal conductivity of the polar phase, and you have this discontinuity here because here there's a phase transition itself of the polar phase itself. The polar phase below 220 Kelvin as a rhombohedral structure. Above that, it's orthorhombic. Okay, you don't care about that. It's just two different structures, but both of them become unstable when you put a mobile charge in the conduction band and you stabilize the cubic phase. And so what is interesting is that a particular at room temperature can indeed experience a considerable change, which is around 30% of the thermal conductivity. Again, not huge, but is there. Okay. Now we have preliminary results with barium titanate, which are very much alike. What is not that cool is that barium titanate has a very slow response. But what is cool is that why I know that they have a slow response, because here in the same institute, there is the group of Ignacio Fina and Florencio Sanchez that they did that experimentally. So they didn't measure the thermal properties, but they experimentally demonstrate they can stabilize the cubic phase by illuminating the sample by photoexcitation. And the other reason that why it's interesting is that barium titanate is one, again, together with that titanate is the prototypical ferrite perovskite that everybody knows, and everybody knows exactly how to treat. But again, the absorbance of barium titanate is very low, and so the response with light is still quite long. So this should be improved. This is maybe a little bit technical, but connects very well with the beginning of my presentation, because once we measured, well, we computed this difference in thermal conductivity between different phases, we went back to that formula, the formula of the phonon train, and we were checking bit by bit where the change came from. And as I anticipated back in the beginning, almost in every case, the culprit is the lifetime. And this is a plot where I'm plotting the difference between the lifetime of the polar and non-polar phases, and you see that throughout all the spectrum, the polar phase has a longer lifetime, and so larger thermal conductivity. And here we compute the effect, we compare the effect of stabilizing the cubic phase in this unconventional way, so with this photoexcitation scheme, or the usual and already experimentally demonstrated case of increasing the temperature. In this case, apparently the mechanism seems to be like equivalent, because you get so all the plots are just the same, but this is very material dependent. So for instance, in this preliminary results we are obtaining now with barium titanate, we have seen that this is not the case, and so you have completely different behavior. So this is not significant, is not general at least. Okay, and this again, if you really paid attention and memorized all the slides I've shown you so far, in that big slide when I claimed that I were addressing only a tiny little bit of the puzzle, so conduction, insulators, phonons. Here I have to make an exception, because if I start putting electrons in the conduction band, in principle, I'm no longer allowed to assume that electrons will not contribute to thermal conductivity. So we computed the effect of the electron thermal conductivity, and we're able to show that it is an order of magnitude lower than the phonon contribution. So it's still a lattice thermal conductivity dominated problem. So this is the conclusion of this part and of the talk that I presented today. This is I mean, the thing that you are most interested right now. As I mentioned, we have a preliminary result with barium titanate. Now we are studying some bidimensional materials. We have results with the charge density wave materials, which is a different distortion of the lattice, different from the ferroelectric distortion, but that can be suppressed by the use of light. And now we have just started studying two-dimensional ferroelectrics like indium selenide, because there the idea is that, okay, that effect I've shown you is cool, it works, at least it has been demonstrated experimentally with similar materials. But if you want to think in terms of efficiency, when you have your thin film, your bulk material, when you shine a light on the material, only the penetration depth of the light will be susceptible of altering the property of the material. So in principle, you have to waste some material to have the effect only in a small thickness. So 2D materials, few layer bidimensional van der Waals material would be an alternative to that, because there all the light will be captured to your active material, and in principle you are more efficient. And this is why now we are targeting bidimensional ferroelectric materials or layered materials exhibited at charge density wave. So that's the summary of this. I mean, the summary cartoon of this dynamical modulation thermal conductivity part. I show you manipulation of a polar lattice by electric field, something newer with light, and just a snapshot of what we did with magnetic fields, but no more than that. I was thinking about stopping here. This is the acknowledgement to the funding and to the many people that helped me with this. And then, of course, I thank you for your attention. Thank you. Thank you at home.
Thanks very much, Riccardo. Are there any questions in the room? Yeah, Matti, through here so that people.
I have one question related to the coherent phonons in superlattices. In particular, you show this this graph in which you have a decreasing thermal conductivity with the periodicity of the superlattice, and then at certain point it increases again. So this thing is like, so why for that period you have coherence is related, is like cavity modes, or it can be an analogy with a laser?
Yeah, I think so. So the thing is that, I mean, speaking, I said that the period gets shorter or get longer. The correct way to say it is that it gets shorter or longer with respect to the mean free paths of the phone.
So for another material, you would have it at
a different point. And also, of course, it's temperature dependent, because the mean free, so the stops, your train stops depends on the temperature. So if a phonon travels a long distance between scattering events, it will not experience, it will tend to experience that as a material. Think, I mean, something revealing, if you think of like gallium arsenide, for instance, or any 3,5 semiconductor, if you go along the 111 axis, you have a layer of gallium and a layer of arsenic. A layer of gallium, that's a superlattice, right? But when you measure, that's gallium arsenide. It has its own electrical conductivity, thermal conductivity, everything. So it's one single number.
Different thermal conductivity.
So that's an artificial lattice.
Yeah.
So if you are able, of course, what is the challenge? The challenge is that you have to have it very short period, and your interfaces have to be very clean, because if they are not clean, at every interface you are randomizing a phonon population and you lose all this beautiful coherent effect. It's very difficult to observe. Actually, I mean, there have been a 2012 paper where they did it with the thin films, I mean, like 2D stacking, and these results are now with the nanowires, but it's not that common. Nanowires are cool in that sense. I mean, they are not cool because you have the boundary scattering, which is a very powerful scattering source in nanowires, and this has nothing to do with coherence, so it can blur out your coherence effect. But it's nice because in nanowires it's possible to have these very clean interfaces, virtually atomically sharp, and so that makes easier to observe this coherent effect.
And another question is, have you considered to have this dynamic control with ferroelastics? Because if you say that the strain is one of the major...
Yes, so I never did that. So I never did that because I tend to think about a way to have an ultra-fast commutation between phases. So strain, of course, works, but the response would be slower. Where I like strain is, for instance, to bring a material in a sweet spot just next to a transition. For instance, in this perovskite, you have, imagine the polarization is upward, okay? Then you start applying biaxial strain, okay? This polarization at one point will fall and will be in plane rather than out of plane. So if you, of course, then you can use it, strain, control the polarization and then the thermal properties and so on. But that would be slow. Now imagine that you simply grow your ferroelectric thin film on a substrate so that the strain is such that you are very next to the spontaneous rotation of the polarization, but not yet, okay? So there you just need a small push to make it rotate, right? So it's sometimes at conferences, imagine your worst referee that it's always rejecting your papers. You want to, kill him. Then I realize it's not a very nice example, but you push it at the edge of a cliff, okay? So the strain is taking him or her next to the edge of a cliff, and once he's there, you just need a push. And so this is very, I mean, not to kill people, but to rotate polarization, because you use the strain not as an active control signal. It's just in electronics, the polarization current. It's the current that fixes the operation point of a device. And then you use the small signal to modulate around it. So that's where I see more interesting, of course, the other also would work. and perhaps you are also able to get to large changes of thermal conductivity using string. But if you think of a fast modulation of the signal, maybe it's not the best way.
You have ferroelectric that are ferroelastic as well. So you can maybe
Combine, yes.
control the ferroelastic domain.
Exactly, yes, yes.
I'm curious about the techniques that you use to model the systems. One question for me is, what technique do you use to model the effect of light? And my second question is that you mentioned in one slide that you use molecular dynamics, Amabilino, force field, and another slide, the Boltzmann equation. My curiosity is, in which cases do you use the Boltzmann equation, and in which ones you use molecular dynamics?
So molecular, I start with the second questions. Molecular dynamics, in principle, you can use it always, okay? The limitation of molecular dynamics is that, I mean, it has to rely on some force field. Now, I mean, like 2 or 3 years ago, this force field was like very delicate because they are semi-classical, parameterized. Nowadays, every kid in high school parameterize them with machine learning techniques, so maybe things have changed. But in principle, I go to molecular dynamics when there is no other tool to do that. So if you want to study domain walls, you need to build a supercell, you need to create your defect, and so if you go to any bulk material, so anything that is represented by a unit cell of 2 to 10 atoms, I do Boltzmann transport equation, which of course you can do with relying on forces computed with a semi-classical force field, but in any case you can usually afford it to do with Amabilino. Okay, light, it's a delicate question. Of course, it's very complicated to do it properly. Now we are using a trick that we believe to this extent it's good enough. So we are simply playing with the smearing of the Fermi distribution. Okay, so the theoreticians that first demonstrated this effect in ferroelectrics did something very elegant with constrained fractional theory, delta, SSM method, whatever. But then in the supporting information demonstrated that at a qualitative effect, you capture the effect. We just need to stabilize the structure. So it's a computational trick. Therefore, I am not able to tell you what laser power you need to have that density of electrons in the conduction band. What I can tell you is that once you have that electron density on conduction band, that thing will happen, maybe.
Great, thanks very much. Are there any other questions? No, I don't think so. How about the people online? Do you have any questions? If so, you can just write in the chat.
No, this is maybe this is.
Okay, Pep, we're just reading your question.
By using light, you can go from ferroelectric with a given polarization to a paraelectric phase. But when cooling back, you will have always ferroelectrics with polarization up and polarization with boundaries. Okay, well, this I don't know because I'm not expert enough in ferroelectric. So I see your point. You shine a light, you stabilize the cubic phase, and when you remove it, you will have a domain structure. Yes, this is possible. I mean, this is the one, you are the one that knows it, because I think you did a large fraction of the experiments I mentioned. So I don't know, that is possible. Maybe also you have a domain structure when you start. So I mean, I assume that that is the situation, because it's what you mentioned in your question. So what we have done with in collaboration with the French group is that they were but that was different because it was an electric field. So I guess that the thing is that when you will come back, it will never be monodomain, but you should be able to control perhaps the fraction of polarization up and polarization down. If they balance completely, well, you have the effect of the domain walls, but in principle, each domain with P up or P down should behave similarly. I mean, if tomorrow you're around for lunch, we can discuss it.
Great, thanks very much. Was that okay, Pep? Let's assume so. Yeah, good, okay. Are there any other questions? Yeah.
Just wondering out of curiosity, in the niobate, you use that because it works and the titanate doesn't work? It's a general thing?
Yeah. With lead titanate, this effect is a bit different. So when you shine a light, you are not able to fully stabilize the phonon dispersion. You just move the instability one point of the plurinsulaton to another. I don't remember correctly. At that time, we just wanted a material where this worked because I need a fully well-behaved phonon dispersion to make the thermal conductivity calculation. At that time, we didn't have the technique. The obvious solution was going to barium titanate, but with barium titanate at the moment, I mean, there was a technicality that we didn't know how to do, so that was the cheap alternative. Now we know how to treat well also barium titanate. I mean, you just have to compute phonons at a finite temperature, and we were learning to do that at that time. So we went to this material, which is simpler.
And when you consider these processes, you consider using high energy light, or the energy doesn't matter, they don't care?
No, the energy, I mean, at least at my very elementary understanding of the problem, you just need an above band gap excitation. So the energy of the light should be sufficient to bring carriers to the conduction band.
Great. Any final questions? No? Online? I don't think so. Okay, if not, let's thank Riccardo again. Thanks very much, Riccardo, for the great talk.